How's it going, Science 10s? This is Mr. Walton here. Today we're going to be talking about the first law of thermodynamics, otherwise known as the conservation of energy. Oh, yeah. We were talking about this a little bit yesterday about how mechanical energy is conserved, and so how we can swap back and forth between potential energy and kinetic energy. Now, today we're going to kind of suss that out a little bit more explicitly. So we're going to go through a definition and then go through kind of some equations, and then we're going to work out some problems, and then blah 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 blah. It's all good. So kind of the definition of the conservation of energy is in an isolated system, energy can change form, but the total amount of energy has to remain unchanged or constant. Now, what I mean by isolated system is that's like energy or matter can't escape it. That's just like a fancy way of making something really ideal, okay? You rarely ever can get an isolated system. It's just kind of this ideal thing to make sure that everything works out perfectly in the end. That's the way you want to think about it. So we're gonna try our best to talk about an isolated system, but we're gonna run into some problems, but that's okay. So the another way of saying what I just said is the initial energy, well, like the energy that you start with, should be equal to the energy that you finish with. That's the idea behind it. And we are going to go ahead and we're going to draw ourselves a roller coaster. First thing I have to do when I draw a roller coaster is I have to draw the ground. Blah, 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 blah. Okay, and then so we're gonna draw a roller coaster. There we go. Perfect. Oh, that looks terrible. Oh man, that looks terrible. But that's okay. That's okay. Everybody, calm down. So here's the start of the roller coaster, and here's the end of the roller coaster. Man, I sure hope you didn't pay money for this. Okay, so what's happening? I don't know if you've ever been on a roller coaster, but typically you start kind of pretty low to the ground and you're going to enter onto, some sort of system of cars or whatever. Here's Mr. Walton. Apparently he's standing up in a car. That's not safe, but that's okay. And what's going to happen is these cars on the roller coaster, they're going to get pulled up this kind of big hill of the roller coaster system. Oops, sorry. And the machine is going to be doing work, like it's exerting a force over a distance, right? And so a machine is going to be doing work by pulling this system of cars up the hill or up the kind of steep incline of the part of the roller coaster. Now, when we get to the top of the hill here, we've got our two cars and we've got Mr. Walton, okay? Up at the top, we've got a very specific type of energy. Do you guys know what type of energy we've got at the top of the hill? Yeah, we got potential energy, right? So at the very top of the hill, we have a lot of potential energy. And where did we get that potential energy from? Well, we got the potential energy from the work that was done on the roller coaster cars. So the work turned into the potential energy. And now, as soon as we go over the crest of this hill, we're going to start to turn that potential energy into kinetic energy. And so way down at the bottom, we're going to get some kinetic energy. And then we're going to go back up, okay? And then over here, we're going to have a little bit of potential energy and a little bit of kinetic energy. So let's kind of think about this for a second. Let's say that as we pull the roller coaster up, right? The amount of work that was done, let's say it was 1,000 joules worth of work, okay? Because work is just energy. That's really all it is. So how much, geez Louise, how much how much potential energy should we have at the top of this hill? Well, if we did 1,000 joules worth of work, then that means we should have 1,000 joules of potential energy. Well, if we have 1,000 joules of potential energy at the top of the hill, how much kinetic energy should we have? Well, we should have 1,000 joules of kinetic energy. Hopefully you see where I'm going with this. And then if we have 1,000 joules of kinetic energy way down at the bottom, right? Because we're going faster and faster and faster as we go down here, and we're going lower and lower and lower. So we're turning our potential energy into kinetic energy, and then we're going to go back up. So we're going to slow down a little bit, right? So we're going to have 500-ish joules of kinetic energy and maybe 500 joules of potential energy. And that total should equal 1,000. Hopefully that makes sense. So at every single stage in this roller coaster, we've got a total of 1,000 joules. And that's what we mean by the energy is changing form, right? We start with work and then potential energy and then kinetic energy and then a little bit of both. But the energy isn't really going anywhere. We're not losing. The total amount of energy at any one point in time should be the same. Now, what we're going to be doing here is we're going to be thinking a little bit more simplistically. And the way we're going to be thinking about it is we're going to be thinking, so the energy initial is going to equal the energy final. Now, what's really important is for you to figure out what type, holy guacamole, what type of energy you have at the beginning and what type of energy you have at the end. And we're just going to dive right into an example here, and hopefully it kind of makes a little bit more sense. So, example number 1, a 1.50 kilogram rock is dropped over the edge of a cliff 30 meters above the surface of a lake. What is the speed of the rock just before it strikes the surface of the lake? So what we want to think about is we want to think about what type of energy do we initially have here, okay? So a 1.5 kilogram rock is dropped over the edge of the cliff. Well, it sounds like to me, so if we had a cliff here and we had, some water down below, so Mr. Walton's got himself a big old rock, 1.5 kilograms. That's reasonably big. And so what type of energy does it start with? Well, he's holding it, so it's not moving, so it's not kinetic energy. It sounds like it's potential energy, right? And then as the rock drops, as it falls, it's going to have a bunch of kinetic energy way down at the bottom. And then it's going to hit the water, and then it's going to lose a bunch of energy, right? So one thing I kind of forgot to mention here is that this roller coaster situation is a little bit of ideal in the sense that, obviously we're going to lose some energy along the way. We're going to lose some energy because of friction between, the wheels or the casters on the roller coaster and the rods that are holding it in place. We're also going to lose some energy because of air resistance and things like that. But when we say isolated system, we're kind of ignoring all of that stuff. Nobody wants to talk about it because it just makes it more complicated. So we're just ignoring that with the fact that we are going to be losing energy here, and whatever, deal with it. It's all good. Okay, so here we're starting with potential energy and it's turning into kinetic energy. So what we have to think about is the initial energy, right? The EP in this case is equal to the final energy, which is the EK. And so we're going to be able to rearrange one of these to be able to find our answer, okay? So let's think about this again. Let's just summarize it. A 1.50 kilogram rock is dropped over the edge of the cliff 30 meters above the surface, so that's the height. 30 meters. What is the speed? V question mark. Okay, perfect. Well, hopefully this kind of makes sense, is that The height is the potential energy, and the velocity is related to the kinetic energy. So what we have to do first, the first thing that we have to do, number one, goodness gracious, what's going on here? The first thing we have to do is we have to find the potential energy, which is just mgh. All right. So 1.50 kilograms times 9.81 meters per second squared, and then times the height, which is 30.0 meters. So that means we have a total potential energy of 441.45 joules. All right. Now, that's the potential energy that we start with, right? So if that's the potential energy that we start with 441 joules, how much are we going to end with? 441 joules. Because the energy can't be lost. You can't gain or lose any energy. It's got to stay constant. That's what it means by conserving energy. Okay, so now we can take that energy, which is now our kinetic energy, and number two, we can rearrange the kinetic energy formula. So EK equals mv squared over 2. We want V. So 2 goes up, m goes down, and we take the square root of it. So V equals the square root of 2 EK over m. So 2 times, well, how much kinetic energy are we going to have at the bottom? We're going to have 441.45 joules. 441.45 joules divided by the mass, which was 1.50 kilograms. And I am totally going to try and show you this on the calculator here, on the calculator, because I think some people are doing this just a little bit wrong. So what I think we should be doing, okay, you could do this in a bunch of different ways. You could do it all at once, or you could kind of do it in a couple different steps. You could go 2 times 441.45, and then you could divide by 1.5. Get the answer, and then you could go here, second x squared, which is the square root, and then go second answer, which is the negative sign, but it's the yellow one. So now we're going to take the square root of our previous answer, and we're going to get 24.3. So 24.3 meters per second. That's how fast approximately the rock is going to be traveling. So that was one way. You could have just done the whole calculation by itself. You could have done square root of 2 times 441.45. Whoa. 0.45, and then divided by 1.5, and that would have been fine. Goodness, I am struggling today. And you would have got the same thing, the exact same answer. Anyways, perfect. So let's just recap this. As long as, if you want to find out the speed, right, which is related to the kinetic energy, then you got to find the potential energy. So we found the potential energy first, then we turned it into kinetic energy, and then we found the speed. We're going to do something a little bit different here. Conservation of energy, example number 2. An average force of 100 newtons is required to pull back on a bowstring a distance of 0.5 meters. The bow is aimed vertically. If the arrow has a mass of 0.0675 kilograms, how high will it go? Man, there's a lot of syntax, grammar stuff that's going on here that's not good. Capital-wise, or a capital letter here, whatever, it's all good. Okay. Let's draw a picture of this. So we've got a bow with a string, and we've got an arrow. I know, it's an amazing drawing. That's actually pretty good for me. So an average force, right? A force is pulling back on an arrow a distance of 0.5 meter. The bow is aimed vertically. That's why it's vertically. If the arrow is a mass, how high will it go? Well, let's think about this. This arrow is going to travel up, and then it's going to reach a maximum height, and then it's going to come back down. So what type of energy does it have at the beginning, right? Because that's kind of what we care about. It's the energy initially equals the energy finally. But we got to figure out what kind of energy do we have at the beginning. Well, what are we doing here? What are we doing at the beginning? Let's go back to our roller coaster. What did we do here at the beginning? We did some work. Work is just energy, right? Work is the energy you give another object. And so here, this is like saying the work is equal to, and what's the energy that we care about at the end? How high will it go? That's up here. That's potential energy. So work is equal to the potential energy. The energy we give the arrow will be the energy it has at the top of its flight. That's the idea. Okay, so I'm going to do some squiggly lines here, and we're going to do this explicitly. An average force of 100 newtons. So F equals 100.0 newtons. Nice. To pull back on a distance of 0. So delta D equals 0.500 meters. The bow is aimed vertically. It has a mass of 0.0675 kilograms. How high will it go? H question mark. Perfect. So if we want, remember the height. The height is related to the potential energy. So if we want the height, what do we have to get first? We got to get the work first. So step number 1, work equals. Well, do you remember what it equals? Here, I'm pulling up our data booklet. What's work here? Well, work here is the force times the distance. All right, no problem. The force times the distance. So force is 100.0 newtons. The distance is 0.500 meters. So the work that we do, 100 times 0.5, is going to be 50.0 joules. Nice. Okay. So that was step 1. So what does that mean? If our work was 50 joules, then how much potential energy are we going to have at the top? 50 joules. We're going to have 50 joules of energy. Not only that, if we do 50 joules worth of work on it, the arrow's going to leave, it's going to shoot out here really quickly with a bunch of kinetic energy, right? It's going to have 50 joules worth of work and 50 joules worth of kinetic energy and 50 joules worth of potential energy. Hopefully you get where I'm going with this. Okay, so we know the potential energy is 50 joules. So all we have to do is rearrange that equation to get height. So if we want height, then that means M and G need to go down here. So height equals EP over mg. So that's 50 joules worth of energy divided by the mass was 0.0675 kilograms. And then G is always 9.81 meters per second squared. Let's do that on our calculator as well, our trusty calculator. So let's do this. 50 divided by, I've got 2 numbers on the bottom. And because I've got 2 numbers on the bottom, I'm going to put them in brackets, okay? Not them in brackets individually. I know I wrote them individually, but I'm going to put them together in one set of brackets. So 0.0675 times all within the same set of brackets, 9.81 end bracket. So we are going to get 75.5 meters. That is the height that this arrow is going to go. So we predict that this arrow is going to go 75.5 meters as long as we don't lose any energy along the way. And that's kind of one of the key steps here. So what I would like you to do is there's technically 2 questions, but also technically 4 questions here. So there's a question 1A, B, and C. And they're very much related to the exact same thing that we just did, okay? They're very related. So you've got this bow. Oh my goodness, that's terrible. You've got this bow. Well, I think that's even worse. Holy guacamole. You got a bow and arrow, and so you're going to be doing some work on the arrow at the beginning, and then the arrow's going to shoot out, right? So the work is going to turn into kinetic energy, and then it's going to go up and then back down. But at the top here, it's going to turn into potential energy. And all of these energies should be the exact same. So the work you do will be equal to the kinetic energy, will be equal to the potential energy. Anyways, you guys get it. You get it. Let me know if you got any questions. So do these 3 questions and then try the kind of the second. You can't see me, but I'm doing air quotes. The second question. So check out the filled in notes for the answers to these questions. As always, I'm available every single day between 10:45 and 11:15. So just swing on by the Google Meet and let me know if you have any questions. All right. See you later.